There are just a couple of formulas we need to look at to finish 5.1. Remember that the definition of a radian is that if you have a length of something, the same length of the radius, I have the length of a rubber band that's the same as the radius, then an arc that has the same an arc of length r subtends an angle of measure 1 radian. So this arc of length r subtends that angle with a radian measure of 1. And if we had an arc of length 2 radians, then it would subtend an angle of length 2 theta. And if we had an angle of 3 radians, it would subtend an arc of 3 times the radius. So if we have any angle of measure theta radians, whatever theta is, it is subtended by an arc of length theta times the radius. 1 radian is subtended by an arc of length 1 radius. 2 radians is subtended by an arc of length 2 radians. So an angle of measure theta is subtended by an arc of length theta times the radius. And this is the formula that we're talking about. It gives us the length of a circular arc. S equals r times theta, where theta must be in radians. Now you have to watch out for that because I'm going to be sneaky. I'm going to give you an angle in degree measure and ask you for an arc length, and you have to remember that to use actually either one of those formulas, theta has to be in radians. So let's look at this first example. If a circular arc of a given length S subtends the central angle theta on a circle, find the radius. Let's just label that radius r, and they're telling us that the S stands for the arc length. So I'm going to label this arc length as 3 kilometers. And we're told that this 3 kilometers subtends an angle of measure 20 degrees. We want to find that radius of that circle. Now remember, we cannot use 20 degrees in this formula. If you give me an angle in degree measure, I have to change it to radians. So again, I'm going to multiply by the unit fraction with degrees in the denominator because that's what I want to cancel, and radians in the numerator because that's what I want to be left with. And we know that 180 degrees is pi radians, so that fraction equals 1. If I reduce that fraction and cancel the degrees, I'm going to be left with pi over 9 radians is the same as 20 degrees. And that's what I will use for the value of theta in the formula. If I substitute into the formula S equals r theta and use 3 for S and pi over 9 for theta, all I have to do to solve for r is multiply both sides by the reciprocal of pi over 9, multiply by 9 over pi, and I get the radius that we're looking for is 27 over pi. And we're not told exactly how to give the measure of r. If on the test I was asked for an exact answer, I'd leave it for as 27 over pi. If I was asked to round it to, say, 2 decimal places, I could punch that on the calculator, and it's about 8.59. So if I have a circle with radius 8.59, and that's kilometers because that's the same units as the arc length, then a 3-kilometer arc length would subtend a 20-degree angle, or an angle of pi/9 radians. Number 32, we're given a picture in the book and I did not have that handy already. Okay, we're given this picture. We have a circle that has a radius of 9 centimeters and an angle that's 120 degrees. And since we can't use 120 degrees in either of the formulas, we're going to change it to radians. I can reduce that 120 over 180 by dividing both by 60 and have 2 pi over 3 radians is equivalent to 120 degrees. So that's what I'll use in the formula for theta. Now, in the A part, I'm asked for the length of the arc. That's S. And S equals R times theta. We're given the radius here is 9 centimeters, and we have theta in terms of radians. So this arc length is just going to be 9 times 2/3 pi, or 6 pi, and that would be in centimeters because our radius is in centimeters. Again, I could punch that and get a decimal approximation or leave the exact answer. I'd take either one on a test unless I specified. The formula for the area of a circular sector, that's the area. For example, in the A part here, it's the area of that circular sector. So the units in our answer are going to be centimeters squared rather than just centimeters, and we're going to use the formula A equals 1/2 R squared theta. If you think about that, it's very much like the geometry formula for finding the area of a triangle. The area of a triangle is 1/2 base times height. Let's see, let me write it up here. But the height of this rectangle would be, or the height of this triangle would be the arc length of the sector. So the base of the triangle is R, and the height of the rectangle is R times theta. And that's where the formula 1/2 R squared theta comes from. So the area of this circular sector is 1/2 times the radius, which is 9 centimeters, times theta in radians, which we found to be 2 pi over 3. I left off my square. Watch out for that. 1/2 R squared theta. That's 81 over 2 times 2/3 pi. Or 27 pi square centimeters for the area of that circular sector. 34 gives us an arc length of 3 feet and a radius of 20 inches. the thing to be careful of there is that our units are not the same in both the arc length and the radius. So we either have to change 3 feet to inches, or we can change 20 inches to feet. I think it would be simpler to say if S is 3 feet, that's 36 inches, because we weren't told whether we had to get our answer. Well, actually, let's see, on the radian and degree measure, our answer is not going to be in inches or feet. Since we're looking for theta, it's going to be given in degrees, and then give the radian measure also. So, we're saying this arc length is 36 inches. Yes, 36 inches. The radius is 20 inches, and here's our angle theta that we're trying to find. If we substitute what we know into the formula, S equals R theta, we'll have 36 inches equals 20 inches times theta, and when we divide both sides by 20, we'll have theta equals 36 over 20, and that reduces by 4 to 9/5, and that as a decimal is 1.8. So that 1.8 is the measure of theta, and we're told that theta has to be in radians, so that 1.8 is 1.8 radians, the measure of theta. Since the direction said give the degree measure also, we're going to say 1.8 radians times pi radians in the denominator equals 180 degrees in the numerator. I just need to multiply the 1.8 times 180 and then divide that by pi. I have approximately 103 we weren't told what to round to, so I'm going to round it to 103.13 in degrees. The B part says find the area of the circular sector determined by theta. Well, now we have R is 20 inches. And that's supposed to be squared, 1/2 R squared theta. Our theta has to be in radians, so we need to use the 1.8 rather than the 103. And we can just punch that on the calculator. Or 20 squared is 400, half of 400 is 200. 200 times 1.8 is 360. Since that's area and our radius is in inches, this is square inches. If we had converted our 20 inches to feet, then this would be in square feet instead of square inches. All right, one last problem. Actually two, but 37's in your homework, and I just kind of worked it out in case you get stuck on it in the homework. Try it without looking at this, but you can look at it if you need to, just because I know a lot of people sometimes are confused about the wording on number 37. Number 36, we're given some angle theta, that's 2.2, and that has to be in radians. And we're given the diameter of this circle is 120 centimeters. Well, neither one of these formulas uses diameter. They both use radius. So if I'm given a diameter of 120 centimeters, I'm going to say the radius is half of that, or 60 centimeters. I think that's the only thing that you have to be careful of in that problem. The A part is looking for the arc length, so we'd use S equals R theta. Theta is already in radians. The B part says find the area of the circular sector. So we'd use A equals 1/2 R squared theta, with R being 60 and theta being the 2.2. I'm not going to punch those on the calculator. I know you could. All right, that finishes up 5.1, so you should be able to do this homework now. Have a good day.